In this video, we'll talk through Theorem 2.6, which gives us a characterization for bipartite graphs in terms of parity of cycle. In particular, a non-trivial graph G is bipartite if and only if it contains no odd cycles. All right, so let's see why this is true. Let's look at a proof of this. So, right, so what do we exactly want to show? Well, we have an if and only if here. So I need to show two things. I'm going to handle the first direction first. That is, I am going to assume, I'll start by assuming that G is bipartite and show that it contains no odd cycles. So I'll say assume G is bipartite. And the claim is that it contains no odd cycles. So what I want to do is give myself an arbitrary cycle and show that it has to be even length. So assume, G is bipartite. Let's let U and W be the partite sets. Let's name them. In particular, no two vertices of U are adjacent, no two vertices of W are adjacent. Be the partite sets. And let C, I'll give myself an arbitrary cycle here. Let's say U1, U2, up through UK, back to U1 is a cycle. Right? And this is a cycle of length K. So in particular, I want to show that K has to be even. All right, so let's give ourselves, let's actually write these out. Let's give ourselves the two partite sets. Here's W, here's U. So without loss of generality, let's assume U1 is in U. So I'll say without loss of generality, assume U1 is an element of U. Right, it doesn't matter if U1 was in W, I would just change the names of these and everything would still work out fine. So there's no harm, there's no loss of generality in assuming that U1 is in U. So here's my U1. And so what does this cycle look like? Well, because there's no two vertices of U are adjacent, the next U2 would have to be up here in W. So this would be U2. Since no two vertices of W are adjacent, the next one would have to be down here. This would be where U3 was. And so on and so forth. You could keep going back and forth, but you have to switch partite sets as you proceed through the cycle. So I'll say observe that UI is in W. So when is this happening? This would be U4 here, by the way. This would be U5. Notice it's the even indexes, which are in W. So UI is in W for all even I. Even index is I. And UJ is in U for all odd I. So now, since my last vertex is U1, that must mean that UK is in W. So UK would have to be here, right? This could keep going back and forth, but the last one, UK, has to be here. So maybe I'll draw some dots there. In particular, K is even. So I'll say in particular. No, I don't want to say that. Since UK must be in W, it follows that K is even. And that's what I wanted to show, right? This is a cycle of length K. This last index K has to be even, therefore the cycle is of even length. So C has even length. Right, and since C was arbitrary, right? This was just an arbitrary cycle. And so any cycle must be of even length. So that proves the forward direction. So let's think about the backwards direction now. So here, I want to assume G has no odd cycles. And I want to show that G is bipartite. So if I want to show that G is bipartite, I need to come up with partite sets. This is where distance comes into play. This is why we have this proof here. So assume G has no odd cycles. I'm just going to give myself a vertex in the graph. Let U be in the vertex set of G. And I'm going to form my partite sets now. So how do I want to form these? I'm going to let big U be the set of all x, all vertices x, so x in the vertex set of G, such that the distance in G between U and x is even. So all those vertices that are of even distance from U go into big U. And I'll let U, hopefully you guessed it, be the set of all vertices such that distance from U to x is odd. Now, notice that this is a partition of my vertices because my graph is non-trivial. There's at least two vertices, and necessarily one must have even distance from U. One must have, and U itself is even distance, and then another vertex would have to have odd distance, so long as I have another vertex in the graph. Okay, so we know G has no odd cycles. We've collected all these vertices, I claim that these are my partite sets. So claim is that G is bipartite with partite sets U and W. Okay, so how do I prove this claim? Well, I need to show that no two vertices of U are adjacent and no two vertices of W are adjacent. So i.e., no two vertices of U are adjacent, and no two vertices of W are adjacent. Now I'm just going to focus in on this case, that showing that no two vertices of W are adjacent. Once we finish, it'll be clear that you can do almost the same thing with U, and so I'll leave that off the proof. We'll just show no two vertices of W are adjacent. So claim, I'll say claim no two vertices of W are adjacent. We're going to do a proof by contradiction here. So suppose not. Let W1 and W2 be in big W, and suppose that they're adjacent. So suppose that W1, W2 is an edge. Right, because I get to assume, right, my assumption is that G has no odd cycles. So what I'm going to try and manufacture here is an odd cycle. I'm going to use the fact here that two vertices of W are adjacent to generate an odd cycle, contradicting our assumption that it has no odd cycles, and that will mean that no two vertices of W are adjacent. Okay, so we have, try and draw a picture for this. So we have this vertex U, we have W1, we have W2, and we know that the distance from U to W1 is odd, and the distance from U to W2 is also odd. So what I'm going to do is I'm going to find geodesics from U to W1 and U to W2, and I'm going to use these to generate an odd cycle. Right. So I'll say let P1 be a UW1 geodesic, right? A path of shortest length. and P2 be AU W2 geodesic. So let's say P1, what do I want to name these vertices? I don't think I even want to. I don't think we need to get into the nitty gritty of what all these are. We can argue this without these. So it's possible that P1 and P2, even though they're geodesics, it's possible that these share some vertices. So it's possible that like I go from U to another vertex, maybe to another vertex, and then they split off and go to W1 and go to W2 like this. Or it's possible that maybe they don't start off the same, but then they come together, they share a vertex. But eventually, since the last vertices of the two geodesics are different, at some point there's some last vertex in P1 and P2 that's shared between both P1 and P2. So I'll say let Z be the last vertex that P1 and P2 have in common. Right, like I said, it's also possible that we come off of U and maybe we split. Here's P1 is going over here, and then they come back together, something like this. And still, this would be the last vertex that they have in common. So this is possible, something like this, but at some point they'll have a last vertex in common. I'm calling that vertex Z. So I'm going to let P1 prime. So I sort of want to throw out this first part of the path, and I just want to focus on the last part of each path, that is Z to W1. Let P1 prime be the subpath. Let me be more specific, be the Z W1 subpath of P1, and P2 prime be the Z W2 subpath of P2. So that is, my P1 prime is this is P1 prime, and my P2 prime is this, P2 prime. So the claim here, all right, claim again, claim P1 prime and P2 prime or the length of P1 prime and P2 prime are the same parity. That is, they're either both even or both odd. So why is that true? Well, remember that these initial paths, P1 and P2, from U to W1, U to W2, that these both had to be of odd length. Now, Z was the last vertex they have in common, so at some point I truncate my path. I just take the end of the path. So I remove, say, the first L vertices of each path. But that's the same number for both of the paths. And so what I'm left with, I can't guarantee that they'll both be even or they'll both be odd, but since I truncate the paths at the same point at the vertex Z, the lengths must be the same parity past that point. So right, P1 prime and P2 prime are the same parity. Indeed, the length of P1 and P2 were both odd. So the subpaths are either both even or both odd. Okay, so cool. So P1 prime, P2 prime have the same parity. Remember though that W1, W2, that these two vertices were adjacent. So let The problem is happening here now. So look at this cycle. This is the P1 prime and P2 prime are the same parity together with Z, right? So if I take two numbers of the same parity, add them together, I get an even number. With the addition of the vertex Z, I now have an odd number. So let C be the cycle obtained by joining P1 prime and P2 prime together with the edge W1, W2. Then C has odd length, right? Since P1 prime and P2 prime were the same parity, that part of the cycle must be even, but now I have this extra vertex Z, or this extra edge, I guess you could say this extra edge W1, W2, which forces this to have odd length. So C has odd length. This contradicts our assumption that G has no odd cycles. Hence, G has no odd cycles. Or, sorry, hence W1, W2 cannot be adjacent. So hence, there are no edges, or I'll say any two vertices of W cannot be adjacent. So that is, we just proved, which claim did we just prove? We just proved this claim, that no two vertices are adjacent. And so that shows that W, no two vertices of W are adjacent. Now, I didn't talk about showing that no two vertices of U are adjacent, but it's the same idea as this. You'll have to pick a vertex in W and essentially do the same thing. So I'm not going to write out the entire argument. It should be clear why that's true. That is, without loss of generality, we can just show no two vertices of W are adjacent. So no two vertices of U are adjacent, no two vertices of W are adjacent. Hence, U and W are partite sets, and G is bipartite. No two vertices, sorry, I keep saying this, of W are adjacent. Similarly, no two vertices of U are adjacent. Hence, G is bipartite. And that's the proof. All right, we'll do some more with distance. We'll define some new terminology goes along with distance, and I'll put that in the next video. All right, see you there.